everyone to the NCTS Algebraic Geometry seminar. Today we are very happy to have Giovanni Inchiostro from the University of Washington. So he's going to talk about weighted blowdowns. Yeah, please.
Yeah, thank you very much for having me speak here. I'm very happy, in fact. Okay, so what I will be talking about today is weighted blowdowns. This is a joint project with Veronica Arena, Andrea Di Lorenzo, Siddharth Mathur, Michele Pernice, and Steven Obinna. And the way I would like to start this talk is to, well, most of the things I'll say will hold in only in characteristic 0, with the exception of maybe a few things at the beginning and throughout the talk. But just for simplicity, let's stick ourselves to characteristic 0. Okay, so I would like to start with this talk by recalling a theorem that probably many of you know, which is Castelnuovo's theorem, which goes as follows. So you start with X, which is a projective surface. And you take a curve E, which is isomorphic to P1, and with self-intersection -1. And then Castelnuovo's theorem tells you that this type of curves can only appear in one way. In other terms, then there exists a map pi from X to X prime, which is a blow up. And X prime is a smooth surface. And the E is the exceptional of the map pi. Okay, so what we'll do throughout, what we'll do later is just generalize this theorem in much bigger generality. But maybe what I would like to do for the first part is just recall you how the proof for this theorem goes, because then we'll see how to squeeze it out and like generalize it in a more general setting. So the proof goes kind of goes as follows. So sketch. So you start with L, which is ample on X, and then up to replacing L with some multiple. You can also assume that HI of L tensor D is equal to 0 for every D greater or equal than 1, and for every I greater or equal than 1. Okay, so you have this L here, and then since L is ample, you're going to have that L restricted to E is going to be isomorphic to O of P1 of some K for some K greater than 0. Okay, so the theorem kind of starts like this, and then says consider L of E, the twisted L by the Cartier divisor given by E, and if you put it in this exact sequence, you have L of E, and here we have O of P1 of K minus 1. Then you have from this that you have that H1 of L of E is equal to 0, just taking the long exact sequence associated to cohomology. Okay, so this applies to L of E. Well, you can do the same, except replacing this sequence with twisting by 2E rather than E, and if you do the same, you can take this sequence, L of E, L of 2E, or P1 of K minus 2. Okay. And from this taking the long exact sequence in cohomology, you'll have that H1 of L of 2E is going to be 0. Okay, now you probably get the pattern. Here you can iterate, and just iterating, you will have that, by induction essentially, that you'll have that H1 of L of ME. This is going to be 0 for every M which is less than or equal than K plus 1. From every M less than or equal than k plus 1. Just iterating. Okay, so where does this lead us to? Well, how the proof of Castelnuovo's theorem then keeps going is as follows. You take essentially what you want to do. You want to contract E, right? And so you need to take some line bundle which contracts E, because that X prime is going to be projective. And so here's the line bundle you take. L of KE is base point free. Okay, and so why is that? Well, it is base point. It agrees with E. So because you have a map from O of L to O of KE, and so this shows it's base point free away from. So here what am I trying to say? This is not L. You have a map from L to L of KE. That's what I'm trying to say. And so the sections of L will separate the points away from E, and once it is restricted to E, you're going to have that L of KE restricted to E will agree with O, and since you have a cohomology vanishing, you can essentially extend the constant functions. Okay, and H0 of L of KE subject to H0 of L of KE restricted to E from our cohomology vanishing. Okay, so this this line bundle is base point free, and what you can do is you can take this the corresponding X prime, and so you can take X prime to be proj of the sum of this line bundle here. You take the global sections. Okay, and so this will give you a map from X, this line bundle will give you a map from X to X prime. Okay, and so that's the first part of the Castelnuovo's theorem, and then what you need to show is you need to show that X prime is smooth. And so here is the idea to show, this is one of the ideas on how to show that X prime is smooth. Is one of the tricks is to use the following, so recall that if you have X, maybe Y, which is a surface, and you have D in Y, which is Cartier divisor inside Y, and you have a point in D, which is smooth, in D, then this will also be smooth in Y will also be smooth. Okay? If you have a surface and you have a Cartier divisor with a point, if the point is smooth in D, then it will be smooth. It will be smooth in Y. Okay, so one way to show that X prime is smooth is to find some curve which passes through. So we have this curve, we have this exceptional here, which is contracted. And one way to show that X prime is smooth is just to find some curve which passes through the point downstairs and which is smooth. Okay, so here is the way that this is the way that it is. I mean, that's at least one way to do it. So you can take some divisor D, which lies in H0 of L of K minus 1E. Okay, such that D restricted to like some global sections here, such that once you restrict it to the exceptional, is just a point. Okay, and why does such a D exist? Well, because we have all our cohomology vanishing. So you know that this line bundle restricted to the exceptional is O of 1, and so you can extend the section, for example, X0 is equal to 0. You can extend it to a global section over here. Okay, now you have to now you have to prove a few things which are not too complicated. So the first one is that D is smooth at X. Maybe let me call this single point X. And you have to show that D mapping to X prime is a closed embedding. Okay, and then you have to show that D mapping to X prime is Cartier. Okay, and if you can show all of these three things, which are not that complicated, once you have that D, then you're going to have that. Then you're going to have that your X prime is going to be smooth at the point pi of X. Okay, so maybe let me just say in words how to prove one of them. So say that you want to, the way you show, for example, that this D is smooth at X. Well, at X, you kind of use the same principle that you kind of use the same commutative algebra fact. It restricts to a Cartier divisor to something which is smooth because it restricts to X0 is equal to 0. And so that's one way to prove it is smooth at X. But okay, so what I'm trying to communicate here is that the proof kind of goes in two ways. There is the construction of X, that you essentially have a line bundle which you show its base point free, and then to prove that the corresponding X prime is smooth, what you do is you look at where the exceptional gets contracted, and you need to find some nice Cartier divisor passing through them, passing to the point which is contracted, which is smooth. Okay, so if you stare at this proof for long enough, well, you can see a bunch of ways that you can generalize this. So here let me see. So here the core idea is, if I can do the swap. Here we go. Okay, so the core idea of the proof, well, it relies, the core part of the proof relies on these cohomology computations, which in turn relies on knowing the cohomology of what we want to contract. Okay, so that's one of the core steps. So know the cohomology of what we want to contract. In particular, we need that it is 0. We need that the desired one is 0. And then 2, to check smoothness, the idea is to slice with a Cartier divisor. To check that your thing is smooth. Okay, so and if we look at this for, if you look at this slicing part at least for some time, you see that kind of what is happening is that how is this Cartier divisor constructed? So you had your surface X, and then you had your E. Okay, and so this E is P1. And then you take, so how was this D constructed? Now on P1, you take the section which is given by X0 is equal to 0, this point here. And our cohomology computations tell us that you can extend that you can find some divisor which cuts it exactly. Okay, but if you stare at it for long enough, what you're kind of doing is, okay, maybe let's just isolate and just look at this divisor. So this is just a curve, and you have a point here. So if you, instead of pretend that this is P1, let's pretend for 1 second that this is PM. Okay, and say that we run the same argument. Let's assume that you can slice it at X0 is equal to 0. And so on this Cartier divisor, you're going to have a Pn minus 1. Pm, whatever it is, m minus 1. Okay, and so if here you can, so this is embedded like this. And so if here you can contract it, maybe you can run some similar argument that where now you use induction, where now on this thing you just contract the Pm minus 1. And so the hope, and so the idea is to think of a point on a curve on this D as just the exceptional of a blowout of the blow up of the same point on the curve. Okay. Okay. So these a few things that I want to say on Castelnuovo's theorem. So the idea is, well, the statement is that if you have a negative curve, a -1 curve on a smooth surface, you can always contract it. To do that, you need to control the cohomology of P1. And the argument for checking smoothness kind of works by slicing with a Cartier divisor. And so what I would like to do now is I would like to generalize this theorem in two directions. One is in arbitrary dimension, where I kind of sketched what is the core idea here. And two is I would like to generalize it in the realm of stacks. Okay? So for doing so, maybe let me, since I'm not sure. Yes. Yes, that's a great point. So we use the self-intersection is -1 because we want a divisor D which hits only on one point. You need that L of KE restricted to E is 0, and if I do K plus 1, it's not 2 or 3 or something, it's just 1. And so I can take the function x0 on the exception, which will vanish at one point, and extend that. Yeah, that's a great question. Yeah, because essentially I want something a curve which cuts transversally on my D, on my E. That's why. Yeah, the same proof goes through if you replace. I mean, for constructing X prime, the same proof goes through if you assume that if you replace 1 with M, except that the smooth part will not go through. Okay, so so there's two directions where I want to generalize this theorem. One is towards the realm of stacks, and two is in arbitrary dimensions. So maybe let me recall you a few things. Now I'll say a few things about stacks in case it's new for some of you. So here's what I want to say. So stacks. This will be just a crash course on algebraic stacks. So it goes as follows. So let's maybe give a few examples. So let G be a group acting on a scheme X. Okay. Then from this data, you can construct a quotient stack. X divided by G. And you can think of it in various ways, but maybe let me just give you the formal definition. So the stack X divided by G so represents the following functor. So hom from B to X divided by G. So this is the same as the following data, is the same as G torsor, so E over B. Maybe this is pi, with pi being a G torsor. Okay, together with a map F from E to X, which is G equivariant. Commutes with the action of G. So this is a G torsor. It means that locally on B is just a product. It's just the base times G. And you have an action of G on E, which essentially commutes with the product, like locally commutes with the product structure. So it's essentially along the fiber. And I want this map F to be G equivariant. So E will have an action of G. X has my action of G. And I want the map F to commute with G. Okay, so let me give you, so what I would like to do for the next 5 to 10 minutes is explain a little bit the ideas behind here, just to introduce stacks, and because they will appear, they will appear later on. Okay, so let's do that. Here we go. Okay, so maybe let me make a few remarks. So, what is the idea of the quotient stack? So if X, let's do a simple case. So say that if X admits a morphism, from X to Y, that is already a G torsor. Okay. Then, so in other terms, when G acts on X as nicely as possible, like for example, when X is Y times G, okay, that's the simplest situation you can think of, or more in general, when you have a map which is a G torsor, then I would like my quotient stack to be Y. And in this case, I mean, you can check from the definition that X divided by G is the same as Y. Okay. So when you have a radial G torsor, the quotient is already your Y thing, and so a quotient stack, a quotient stack in general is just a formal replacement of Y when Y does not exist. That's one way to think of that's one way to think of a quotient stack. So if your action of G on X is as simple as possible, it's a torsor, then you should have just the base. And then a quotient stack is just a formal replacement of the base when you don't have it, essentially. Okay, so that's one of the few remarks that I want to make. So here's the second one. That you have a map from, if you can check that you have a map from X to X mod G. Okay, and you can think of this as being the universal torsor. So it's universal torsor. Okay, in other terms, in other terms, this diagram is fibered. So if you have a map from B to X mod G, so remember that this data here gives you your E and your F. Okay, so let's just put them in. So now you have your pi here, and you have your E, and this map to X. Okay, and now if I take the map from X to G to be the natural projection, maybe you can call it P. You can check that this diagram here is a Cartesian diagram. Okay, so you can think of this E as the pullback of the universal torsor over X mod G. That's another way to think of the stack X mod G. Okay, and maybe the third thing that I want to say, which is probably the most useful for us, is an example. And here I'm out of chalk, so maybe here we go. Oh, in fact, I have this one. I like better this one. Okay, so this is the example number 3. So say that G is finite and X is affine. Okay, then what you can do is you can do the following. So you have spec A. So this is the universal torsor over the quotient stack. It is the same as the P that we constructed before. And now you can check that this quotient stack will map to the other to another quotient, which is spec of the ring of invariants. Okay, so this is the ring of invariants. Okay, and all the quotient stacks all the stacks which we will find, all the stacks which we will find, X will satisfy the following condition. Will satisfy the following condition that they will admit a map to some X, which is usually called the coarse moduli space, which locally you can find a smooth atlas, with this being spec A and this being spec A divided by G. So what am I trying to communicate? I'm trying to communicate that while I didn't tell you how all stacks are look like, if you only understand quotient stacks, for this talk, it's essentially enough. Because all the stacks locally will be just these quotient stacks, with this diagram being Cartesian. This is the square diagram. Okay, so these are a few things that I want to say about stacks. Essentially, I want to say two things. One, what quotient stacks are, okay, and you can think of them as a quotient stack. If the action of G on X is as simple as possible, then X is going to be some G torso over Y, and the quotient is Y. A quotient stack is just a formal replacement of Y when such a Y does not exist. First thing I want to say. Second thing I want to say that all the other stacks that will appear here, they will have this local property. They will map to some scheme X in a way such that locally over the scheme, they will be quotient stacks. So if we understand quotient stacks, we understand everything that is there to understand about stacks in this talk. Okay, so questions or comments? Yes. Oh yeah, because here probably maybe I did not want to use curly X as a notation. Sorry, maybe let me just call it curly Y. I'm saying take any a stack, so all the stacks which will appear. Let's say, let me denote them with dummy variable called curly Y.
Spec A should be the spec of the G invariant part of the.
Yeah, exactly.
You have the in the Cartesian diagram down so below. Yeah.
Oh yes. Oh yes.
Yeah.
Thank you. Yeah. So this wants to be the G invariance. Yeah, it's this picture over here. And okay, yeah. So these are the two things that I want to talk about, at least for the first part of the talk. So one is Castelnuovo's theorem, and this proof of Castelnuovo's theorem, which requires, which is essentially the idea is to prove smoothness. You just find some Cartier divisor which passes through the point that you want to be smooth, and you just show that your Cartier divisor is smooth. And the second thing is I want to introduce you a little bit of stacks. And for the second part, the bottom line is if you understand quotient stacks, and quotient stacks are, the definition is not that complicated, then you will understand essentially all the stacks which appear in this seminar. Okay, questions or comments? Yes. Correct. For this topic, so the only stacks that you'll see are quotient stacks explicitly, where will be either quotient stacks or stacks which locally will be like this for G being a finite group. Yeah. Other questions? Okay, so let's see where are we going. So maybe let me write down here the theorem that I want to prove. So theorem goes as follows. And this is joined with the same people as before. So here there is Arena, Di Lorenzo, Mathur, Pernice, Obina. Well, myself, I guess. So Veronica Arena, Andrea Di Lorenzo, Siddharth Mathur, Michele Pernice, and Steven Obinna. And so the theorem goes as follows. So what I'll do now is I will just write down the general statement that we're going to spend the rest of the time patching up and making sure that we understand what's written on the board. So the theorem goes as follows. So say that you have, where is it? So say that you have X and Y. So these will be the Lim-Mumford stacks. That are separated and smooth. Okay, say that you have pi from E to Y, which is a weighted projective bundle. Okay. And after I will explain all the words which appear. Okay, and say that you have an inclusion of E inside X, which is a Cartier. So locally it's cut out by a single equation. And you want that OX of E restricted to one of the fibers. It should be O of -1. Okay, and so in this setting, let's see what happens. So we have, let's draw a little diagram. So we have our curly X, and then we have the Cartier divisor inside curly X, mapping to curly Y. Okay, so in this setting there exists, so there's three things that I want to say. The first one is that exists a Z fitting here. Okay, so you have okay. Then Z is like all the other stacks. So Z is smooth and separated. The Lim-Mumford. Okay, and then the third thing is that maybe I can call this map pi of X. Pi of X is what's called a weighted blow-up. Okay, so what am I trying to communicate writing this? So I guess on a first approximation, this is a generalization of Castelnuovo's theorem. Okay, it's generalized to arbitrary dimensions and to the realm of stacks. And what we will do now is we will go through the statement, and whenever we find some words that need some explanation, I will explain what the word is saying. Okay, and maybe before doing that, let me give you a few applications to like motivate why this is an interesting result beyond generalizing Castelnuovo's theorem. So one of the corollary, I mean, there are a couple of corollaries of this result, so maybe let me just list one. So let delta be the locus, the closure of the locus of curves like this. So this E1, and here you have n points. You can take the closure of this locus inside M1n bar. Okay, so remember that M1n bar is the modular space of genus 1 n-pointed curves. And so you can take the curves which look like this. You have an elliptic curve attached to a P1 with m plus 1 points, and you can take the closure of this locus. So it's not complicated to check that delta is isomorphic to P. It's isomorphic to M11 bar times M0 n plus 1 bar. Okay, and just applying this theorem, kind of, it's a kind of a straightforward application of this theorem that you have a contraction map from M1n bar to this modular space M1n pseudo-stable, okay, which contracts delta. Okay, essentially there is a map from the modular space of genus 1 n-pointed curves to some other algebraic stack which is smooth, which contracts this divisor delta. Okay, and just which this follows from this theorem, and from the theorem you can check that this map. Maybe I can call this pi of M1n bar. Pi of M1n bar is a weighted blow-up. Okay, so what I'm trying to say is that this theorem applies to kind of directly to some results on the moduli space of curves, in particular for the moduli space of genus 1 and pointed curves. Another application of this result is to a similar statement for the moduli space of weighted curves, like the Hassett moduli space of curves, in case you are familiar with those. Okay, so what I'm trying to communicate with these two boards is two things. One is that it's a generalization of Castelnuovo's theorem to higher dimensions and to the realm of stacks. And two is that you can just apply this theorem right away for the case of curves to have contractions for M1 n bar. Yeah. Yes, this gives correct, exactly. So this gives another compactification of the smooth M1n. Yeah. So this one was already known. It turns out this was already known. It was not known. I think it was known it was smooth. I don't think that it was known that the map was a weighted blow up. Yeah. So here we can check it's a weighted blow up with weights 4 and 6. Like you can really write it down explicitly. Yeah. Oh yes, because these are called pseudo-stable curves. It's essentially like you can do this in general for in moduli of curves. Like what you can do is you can quote unquote contract the elliptic tails. Like whenever you have a curve with an elliptic curve sticking out, you can do the curve is the Riemann-Mumford stable. What you can do is you can contract this curve and put a cuspidal singularity here. And that's how you can do this in families. Yeah, I mean, it doesn't follow from the theorem, but the construction of M pseudo, so this map here, so I don't know if this is smooth in general, but the contraction is one of the, for MGN, it was one which already appeared in all the results about the minimum model program from MGN. I'm not sure if in general this is smooth, and I don't think in general it's a weighted blow up, but yeah, for M1N it is. Other questions? Okay, right. So what I would like to do now is I would like to explain everything which appears on this board. So let's do that. Which time I have? 1 hour, 50 minutes. Yeah. Oh yeah. So here I will explain these words. I will explain all the words which appear. Yeah. For now, I understand that just writing this down, I didn't really communicate that much. I wanna fix that essentially. Okay, so let's read this together. Okay, so we start from X and Y to be, okay, what does this word Deligne-Mumford mean? A Deligne-Mumford, well, a separated Deligne-Mumford stack, you can think of it as a stack which kind of looks like that. So first this remark. If Y is a separated Deligne-Mumford stack, this is an M, then so this is a deep theorem, and then the theory kind of goes another route. But I think that for probably pedagogically, the best way to think of it at this point is to think of it in this way. So if you have W, which is separated in Mumford stack, then there is an algebraic space. Maybe let's call it Roman W, and the map curly W to Roman W, such that this Roman W admits an étale surjective morphism from spec A gamma. And here we have our spec A divided by gamma. this diagram being Cartesian, with gamma being finite. Okay, so what am I trying to communicate here? So that's the way to parse this dilemma. If you put these two together, no, not smooth, separated. Interesting. So if you put these two together, that's the way to parse it, okay? So you have X and Y, which admits some map to something that you can think of it as a scheme, which at all locally is like the quotient that we constructed before, okay? Okay, so let's keep parsing. So then smooth. So this is smooth. I'll not say much. It essentially means that all these spec A's are smooth. Okay, and now we have this map from P from E to Y, which is a weighted projective bundle. Okay, so now we should parse what this is saying. So let's do that. Maybe I can do it in a different color. Here we go. Okay, so let's parse weighted projective bundle. Okay, so that's one way. So here is one way to think of it. So okay, so this is going to be about the yellow part. Okay, so recall that you can define Pn in many ways. Pn represents the functor from schemes to sets that sends a scheme X, or maybe X I already used, maybe let's say B, to this pair to L S0 Sn, such that L is a line bundle on B, and then you have a bunch of sections. Si are global sections of L, and they don't vanish simultaneously. Up to some isomorphism. Okay, so what am I trying to say here? So this is just a fancy way to say that giving a map to Pn is the same thing as giving a line bundle with n sections, that n plus 1 sections, that don't vanish simultaneously. Okay, so what you can do now is maybe I can call this functor f. So let me just do a little twist of this functor. So let's fix some weights a0, an, be positive numbers. So these in z to the n plus 1 greater than 0. And then I can consider this functor f. So maybe this is a weight vector a. I can consider the functor f with weight vector a, to which sends b to the following set. I mean, to the following. It's a groupoid, but if you think of it as a set for now, it doesn't. You don't really lose that much. Where you have L, and you have S0, Sn. That's that like before. So L is a line bundle. Okay, and now you have that these Si belong to H0 of L to the AI. Okay, and they don't vanish simultaneously. Is equal to empty set up to isomorphism. Okay, so this is kind of if you think of Pn as representing this functor, it is kind of a natural generalization. You're just asking the sections to be in some power of this L. Okay, so a weighted projective. Go. So the fact is that this functor is representable, and it's representable by what is called a weighted projective stack. So fact Fa is representable by a weighted projective stack. Which maybe I'll denote with P. This is a curly P, and then here one of A0, AN. Okay, so what I'm trying to say is that a weighted projective stack, like a projective space is what represents the functor f. A weighted projective stack is what represents this functor fa. So giving a morphism to fa is the same as giving this data here. That's one way to think of a weighted projective stack. Let me tell you another way to think of a weighted projective stack, because all the stacks that we played around with were quotient stacks. Okay, so maybe remark. So remember that Pn is an plus 1 minus 0 divided by gm. Okay, here, I mean, I cannot just do it like that. Okay, so weighted projective stack. So if gm acts on an plus 1 with weights a0, an, then my weighted projective stack is that P of a0, an is just an plus 1 minus 0 divided by gm. Okay. That's another way to think of a weighted projective stack. So for now, I'm giving you two ways to think of a weighted projective stack. The first one is just generalize like the same way Pn represents this functor, just as a mild generalization of this functor turns out is represented by an algebraic stack, which is a weighted projective stack. Second way I'm telling you that one can think of a weighted projective stack is, well, if Pn is this thing, then P of a0, an is going to be just you put an action with the weights a0, an on an plus 1. This is what a weighted projective stack is. Yes. They're not, in fact. For example, yeah, they are schemes only when they are schemes only when all the coefficients are 1, in which case they are PNs. Yeah, good question. They are at least so now we're working over C, but in general, when all these AIs are invertible in your field, they are the Riemann-Mumford stack. So they locally map to they admit a map to a scheme, which is a usual weighted projective space, and etal local. They cannot look like that. So yeah, in general, you cannot represent this by a scheme. Essentially, because this is not really a set. This is just a group. I'm brushing it under the rug because it kind of deflects the point. I'm sorry. Okay, so this is what a weighted projective stack is, but now I didn't still tell you what is a weighted projective bundle, but it's kind of what now you can guess. So weighted. So pi from E to Y is a weighted projective bundle. If you can do the following, so you have your E mapping to Y, if you can find some etal atlas, this being spec A, and this being spec A times one of these weighted projective stacks. Okay, so this must satisfy these first condition, and now is the second condition, which is a little bit more technical. Let me just write it down for completeness. So there exists a line bundle L on E, such that L restricted to each fiber. This was pi. E of pi of E is O of 1. This one I'm just writing for completeness, otherwise it's a wrong definition. I encourage you to ignore it because it's kind of, it takes out of the point. Okay, so what am I trying to say here when I say weighted projective bundle? I'm trying to say that it's a fibration which locally on Y is just just a product of a weighted projective stack with the base. Okay, so it's just a fibration of weighted in weighted projective stacks. Okay, so maybe let's reread. So we have X and Y, which are separated in Mumford stacks, which are smooth. And then I want this to be a weighted projective bundle, which is a vibration essentially in weighted projective stacks. And then I have my E inside X, which is Cartier. It's a Cartier divisor, so this means it's locally cut out by one equation. And this restricts to O of -1. Okay, so how can you interpret this? Well, these weighted projective stacks, they exactly like Pn, they have a cyclic Picard group, they have Z. And so you can take the generator of the Picard group, which has no global sections, and we just call it O of -1. And I'm asking that essentially this Cartier divisor restricts to O of -1. So you can think of this condition as something that we have already seen. Let's use different color. Here we go. So this is inspired from Castelnuovo essentially. Like in the simplest case where X is a surface and Y is a point and E is just P1, this condition here will be the negativity in Castelnuovo, okay? Okay, so if you are in this setting, so you have this Cartier divisor which admits a vibration, and it's a weighted projective bundle vibration. Then I'm saying that you can put a Z here, Z, which is smooth and separated and then in Mumford. So here is the same as before. So Z will have. Oh, so this is the same condition that we had here. Okay, and now there is this new thing that now I should explain a little bit, and I'm saying this pi x is what we call is what a weighted blow up. Okay, so let me maybe explain a little bit what a weighted blow up is. So let's do, well, maybe first let me stop to see if there is questions. Okay, so maybe let me explain a little bit what weighted blow ups are. So please be a remark about the green, what is boxed here in green. Here we go. Okay, so we'll just do the simplest case, and all the other case will be built from this simplest case, which will be a weighted blow up of the origin. Up of the origin in A2 with weights W1 and W2 with Wi being positive integers, okay? So this will be an example of a weighted blow up of the origin in A2 with these weights, and then I'll tell you how to deduce from this simple case the general one. Okay, so how is this constructed? Well, you do the following, or at least I like doing the following. So consider A3. With the action A3, an action of GM by scaling with weights W1, W2, and -1. Okay, so you can do the following. So you have A3 mod GM. Okay, so this will map to, just forgetting the last coordinate, this will map to A2 mod GM. This is the map which sends A and B and T to A and B. Okay, and here I was acting with the weights W1 and W2, which are two integers. And so inside A2 mod GM, I'll have the complement of the origin. So inside here, I will have the weighted projective space with weights W1 and W2. Okay. And here I can take the fiber product. So the fiber product, you can write it down explicitly. So it's going to be the triples A and B and U, such that A comma B is different from 0, 0, divided by GM is just the fiber product. Okay, and now this A3 mod GM, so these will map, if you just take the ring of invariants, so these will map to A2 with coefficient, so say that, so here, this is the map which sends A, B, T to A, T to the W1 and B, T to the W2. Okay, so now there's a bunch of diagrams on the board. Maybe let me repeat them. So we start with A3 mod GM with the action with weights W1, W2, and -1. And you can just map to the first two coordinates, A and B. This will map to A2 mod GM. Inside this A2 mod GM, there's going to be the weighted projective stack, PW1, W2. That's how they are defined. They're just the complement of 0 inside AN mod GM. And you can just take the pre-image of this open. Okay, it's going to be the triples A and B and U, such that A, B is different from 0, 0. Okay, and this will map to A2, just taking the ring of invariants. That's the map which sends A and B and T to A, T to the W1 and B to T to the W2. Okay, so this is kind of this diagram that one can consider, and here's my definition. So maybe I can call this fiber product. So this fiber product, so maybe F. So the fiber product F is the weighted blow up of the origin in A2 with weights W1 and W2. Okay, so this map from F to A2, maybe I can call this map pi. And so pi is the blow up. Okay, so what am I trying to communicate with these two boards? Well, I'm trying to tell you one way to think of the weighted blow up of the origin in A2 and how to write it down explicitly. And here is how you write it down. You start from A3 and you look at the locus in A3 where A and B are different from 0, 0, and you mod out by the action of GM. With on A has weight W1, B on weight W2, and on the last coordinate has weight as weight -1. So this will map to A2 by the map which sends A, B, and T to A, T, W1, B to the T to the W2. And this thing will be what I call a weighted blow up of the origin in A2. Okay. So now here we'll see a theme which will stay with us throughout the whole talk, which, and I encourage you to think of it, is whenever I say something about weighted projective spaces or weighted blow-ups, if I choose W1 and W2 to be 1, 1, you can check that this recovers the original definition either of a blow-up of the origin or of PN. Okay, so this will be the usual definition of a blow-up of the origin in A2 when you just put weights 1, 1. Okay, so this is what the weighted blow-up of the origin is, and of A2, and maybe remark number 2. You can generalize, you can imagine how this generalizes to AN. Okay. And so what will be a weighted blow up for us? I mean, the definition is slightly more general, but for us, a weighted blow up, so our weighted, technically those are called the regular weighted blow ups. So a regular weighted blow up is something which smooth locally is pulled back from a blow up like that. So for us, a weighted blow up of some y inside Z will satisfy the following condition. So you have a map from y inside Z, and now here you have a smooth map. Smooth. So here you have your W, and now this maps to AN. Okay, and now this is your blow up, and now here you can pull back the blow up on W. And this is the weighted blow up I defined before. So this was my weighted blow up of the origin in AN with some weight W. And all these diagrams should be Cartesian. Okay, so what am I trying to communicate with this? Okay, so maybe what am I trying to communicate with these two boards? Well, one, I'm telling you what is the weighted blow up of the origin in A2. And two, I'm telling you that for me, a weighted blow up will be something that smooth locally is just a pullback of the blow up of the origin in A2. So as long as we understand the blow up of the origin in A2, we understand all the weighted blow ups which appear. And the weighted blow up of the origin in A2 is, we can just write it down explicitly. Okay, so now we should be able to somehow parse all these theorems. So, okay, so maybe let's look at it again together. So I have a separated Riemann-Mumford stacks, which means that they have a map to their coarse moduli spaces, and locally they're just quotient of a finite group. That's what separated Riemann-Mumford stack implies. And for us, we can take it as a definition. Then we have this weighted projective bundle. So what is a weighted projective bundle? It's a fibration where all the, well, you can think of it as essentially a fibration where all the fibers are weighted projective stacks. Weighted projective stack is just a generalization of Pn. And so if you have these two assumptions together with a negativity, which essentially is inspired by Castelnuovo, then you can contract the fibers of E, exactly as you were doing in the case of Castelnuovo. You're going to end up with Z, which should be again a smooth and separated Riemann-Mumford stack. So again, locally is going to be a quotient by a finite group, stack quotient by a finite group. And this map here, I mean, in Castelnuovo, it was just a blow up. Here is what we call a weighted blow up. Okay, so what is a weighted blow up? Well, weighted blow up of the origin in A2, we can write it down. And in general, it's essentially constructed from the weighted blow up of the origin in AN. In general, it means that smooth locally, it's just pulled back, this map being flat. So this map is flat on the, let me just say in words, this map is flat on the preimage of the origin, so it's just a pullback of the weighted blow up of the origin in AN. Okay, questions or comments?
Could I ask a question about the statement?
Yeah.
So if we start with variety instead of the Riemann-Mumford stack, so say X and Y are varieties.
Yes.
In the statement, and
yes.
then E also a
variety,
divisor,
yeah.
which is E is a divisor which is isomorphic to a weighted projective space. So the coarse weighted projective space, and suppose that the divisor restricted to itself is O-1, and in this case, can we contract, or we need?
Let me think. So I'll answer a simple question, but which is not what you're asking. So if this is a variety, and this is a fibration in PNs, then Z will be a smooth scheme. If this is a fibration in weighted projective,
yeah, let's say Y is the point. Y is the point.
Y is the point, and this is just a weighted projective
space. Yes. Can we contract, or we really need start with the Riemann-Mumford stack?
Yes. Okay. So let me. I think my official answer is I don't know, but here's what I think. So here the real content here is not really constructing Z. It's constructing Z which is smooth. As in Castelnuovo's theorem, the hard part was not really constructing the contraction. It's just to check smoothness. I think if you have a weighted projective space and you just want to contract it, I think you can use the results which come from essentially Artin's contraction theorem to construct it.
So as long as you have a negative intersection, something like this.
I wouldn't be surprised. Yeah, I think it's reasonable to believe you can contract it using Artin's theorem. But again, here the real thing is not really to construct something downstairs, is to construct something downstairs which is smooth and to classify the map.
Okay, thank you.
Yeah, it's a great question. Yeah, because so this is something if I had time, I want to sketch at the end. So how does the proof go? Or what is the part that is really a content here? So constructing something down here is not really complicated. This Z, so here I didn't write it down yet, but this Z is kind of the minimal one you can construct. And like the smoothness is really the content here. The fact that this is smooth and the fact that this is minimal in the sense that this is a push out in the category of algebraic stack. Whenever this is kind of the minimal thing you can construct. If you can find some other Z prime here, that this Z that we construct explicitly will map to that Z prime. As in Castelnuovo's theorem, the really complicated part was not really just to construct something downstairs, but to construct something smooth and to classify the map. Okay, so maybe let me see a few things that, let me see how much, I have 20 minutes. So let's see. So maybe let me explain a little bit how this result can come about in a specific example, which is inspired from one of the theorems, which is the example of M1n bar. Okay, so what I would like to do now is, do you do that? Can I swap them? I should be able to. Here we go. Okay, so so one of the applications I was talking about before is to the case of genus 1 n-pointed curves. Okay, so let's do that by hand in the case where n is equal to 2. So this will be what we will do in the remaining part of this talk. Okay, so contraction from M1 2 bar to M1 2 pseudo-stable. Okay, so how does the construction work? So the way I think of it is as follows. So consider the map from A3 to A2, which sends a point alpha 2, alpha 3, alpha 4 to alpha 4, and here I have alpha 3 square minus alpha 2 cube minus alpha 2 alpha 4. Okay, like this map F. Okay, I'll first write it down and then explain why this is relevant. So we can take GM acts on, if you take GM which acts on A3 with weights 2 and 3 and 4, and GM which acts on the target with weights 4 and 6, okay, then this map is GM equivariant, then F is GM equivariant and induces a map between the corresponding quotients from A3 mod GM to A2 mod GM. Okay, so why is this relevant? So I should talk about M1 2 bar. And so what I want to do now is I want to explain why the source, well, maybe this source, in fact, why this source is relevant to M1 2 bar, why this target is relevant to M1 2 bar, and why this map here is relevant for M1 2 bar. Okay, because remember I want to talk about M1 2 bar. Okay, so maybe let's start with the source. So start with the source. Okay, and the source follows from the following fact. Here we go. Every pair E comma P1 and P2, where E is a smooth genus 1 curve. And then we have 2 points with distinct points in E. Every pair like this with a smooth genus 1 curve and together with 2 points can be written in the following equation. Can be written as the zero locus of y square z plus a3 yz square is equal to x cubed plus a2 x square z plus a4 xz square together with the 2 points that they belong to all of these. So let's see, now I'll mess it up. So I want x to be 0. So I think it's 0, 1, 0, and 0, 0, 1. Okay, so this is the first fact. At every pair like this, every pair consisting of a smooth elliptic or smooth genus 1 curve together with 2 points, turns out that you can write it in this form here. Okay, the proof is not complicated. It's kind of well, maybe I'll let you think of it. Just a consequence of Riemann-Roch once you embed into P2, and then you have to move the points around with PGL2. Okay, and so maybe let me call this curve E, which depends on the parameter A2 and A3 and A4. So E will be essentially this pair, the pair consisting of my elliptic curve together with the 2 points. And then the second statement, which is again not that complicated, is that the pair consisting to A2, A3, and A4 is isomorphic to the one A2 corresponding to A2 prime, A3 prime, and A4 prime. This is equivalent to saying that there exists some lambda in GM such that lambda square A2 is A2 prime and lambda cube A3 is A3 prime and lambda to the 4 A4 is A4 prime. Okay, but then if you think of it, what's written here, and you try to formulate it maybe more intrinsically, so this means that there exists, at least at the level of sets, there exists, at least at the level of sets, a map from M12 inside the quotient of A3 with coefficients A2 and A3 and A4 divided by GM. Okay, and it turns out that this map is in fact algebraic. It's not complicated to check this map. I mean, essentially just constructed the universal family over here. So this map is algebraic. Okay, so this is the relevance of the domain. So this is the relevance. So this is why the domain here is interesting for our goal for M12 bar. Okay, so this is the green one. Okay, now I should talk about the yellow one. The yellow one is kind of similar. So the yellow one, all these are not too complicated. I think this is even more classical than the other one. So every pair is of the form E and P, such that E is an elliptic curve. A smooth genus 1 curve together with a point is such that is isomorphic to the pair consisting of the zero locus of y square z is equal to x cubed plus I call it the name, so b4 xz square plus b6 z cube together with the point at infinity, together with, so here z and x must be 0. Okay, and two pairs like these are isomorphic. So maybe, and I can call maybe this elliptic curve the E corresponding to the pair B4 and B6. And the second point is that E of B4, B6 is isomorphic to E of B4 prime and B6 prime, if and only if the same relation as before. So there exists some lambda non-zero in GM, such that lambda to the fourth B4 is B4 prime, and lambda to the 6 B6 is B6 prime. Okay. Essentially, what I'm trying to say is that the same story that I wrote here for the domain goes through also for the target, except it's not M12, but it's M11. Okay. So from this we have, maybe I can just do it here. We have an embedding from M11 inside the target, which was A2 mod GM. Okay, so this explains, let's see. So we had this map that I want to explain it a little bit. So the source has to do with M12 because of this fact. Okay. So every elliptic curve with every curve, just smooth genus one curve with 2 points can be written in this form. So it essentially depends only on these three coefficients, A2 and A3 and A4. And two curves are isomorphic only if the three coefficients are related by this rule. Okay, and so this quotient, if you just mod out by the rule, essentially, this quotient contains M12. And similar story for M11. Okay, M11 is contained inside A2 mod GM. Okay, and so now I should tell you what the map is. So there is a map here, F, and if you think of it, what you can do is you can take a curve like this, okay, and you can just forget this point here. If you just forget the second point, then it's just a smooth elliptic curve together with 1 point, and so you should be able to do some change of coordinate to write it in that form. Okay, that's what fact one. That's what fact 2 is telling you. And so this will explain what the map is, because if you do that, so for the map F, so this is the third remark. But if you perform the change of variables, where you call big X to be small x plus A2, these are small x, A2 over 3, big Y to be small y plus A3 over 2, and you have big Z to be the same as small z, and then you have alpha 2 to be A2 over 3, alpha 3 to be A3 over 2, and then alpha 4, some other change of variable, alpha 4 to be A4 minus A2 square over 3. Okay. If you perform this change of variables, then you can bring this equation into that equation explicitly. So maybe I can label this with a star. And star becomes let's see, y square z is equal to x cubed plus alpha 4 times z square x plus this coefficient times alpha 6, which is A3 square minus a alpha 2 cube minus alpha 2 alpha 4 times z cube. Okay, and this explains the relevance of the map. the map, what is the map doing in terms of families? It's doing the following. Well, if you take a curve like this, well, if you forget one of the 2 points, if you forget this point, you should be able to, from fact 2, you should be able to do some change of coordinate, which brings this equation into something which looks like that. Okay, this is the change of coordinate, and the fibers of this map is essentially how many times you hit an elliptic curve. Okay, so this is so now we have a map like this from a 3 mod GM to a 2 mod GM. So let's try to play around with it a little bit.
But if A2 and A3 are not 0, then the mark point doesn't go to 0, 1, 0, or yeah, I don't know. So
I think it no. Oh yes, I might yes, you're right. I think I'm pre-composed. I think here I'm doing up. Let me see. Did I mess up the change of coordinate? Maybe let me get back to that.
Okay. No problem.
Yeah. Yeah, maybe I think I'm sure if I compute it now, I'll just stare at the board for 5 minutes.
Oh, no problem.
Yeah. Okay, so okay, so let's play around a little bit with this map. So we have the following situation. So we have a 3 mod GM, and this maps to my A2 mod GM. Okay, so inside A2 mod GM, I have my weighted projective stack. That's what we've been doing kind of the whole time. So here we have P of 4, 6. Okay, and you can check that this is the same as M11 bar. You can check this. You can check that this P of 4, 6 contains M11 from the yellow fact over here, or from the yellow fact over here. M11 lives inside here, and in fact it lives inside the complement of the origin, my P46, and my P46 is in fact a compactification, which is M11 bar. Okay, and so here I can do the same story. Here I can do P of 2, 3, 4. Okay, and now if you check a little bit, so this map here is no longer a morphism, but it's just a rational map here. Okay, and okay, so now if those were actually projective spaces, how would you resolve the natural map from P2 to P1? You just blow up a point. Okay, those are weighted projective spaces, and so you don't need to do a normal blow up. A normal blow up would not work, but you can check that this map locally is the same as this map here. So here we had A2 mapping to A3, which the map sends A, B, mapping to A, B1. Okay, and so so this will give you a rational map to P W1 W2. This is the local picture. You can just do a weighted blow up. So here you can resolve this map, essentially coming from the universal family with a single weighted blow up of this point Z with weights 4 and 6 of P 2, 3, 4, and this will give you a map pi. Okay, so what
Too late.
Right, so the theorem here, so I think this was proved by me before we knew all of that. So this is, I think, 21. So the theorem is that this blow up Z with weights 4 and 6 of P of 2, 3, 4 is isomorphic to M12 bar. This here is the, I didn't know it back then, but this is the pseudo-stable compactification of M12 bar. So P of 2, 3, 4 is M12 pseudo-stable. Okay, and so this map here that now I construct explicitly just to resolve the indeterminacy of this map is the same as I told you long ago that exists from our corollary of the main theorem. And the reason I'm deciding to present this last result is kind of in the philosophy of okay, so you can do these constructions on these moduli spaces and why they generalize Castelnuov's theorem, which is a very important result, but what can I actually do it in practice with it? And so maybe let me show you what I was able to do it in practice with this explicit description that maybe can tell you something about M12 bar. And so the philosophy is the same as the philosophy under many of the results of the minimal model program, which is why do we care about doing these constructions? Because this space is simpler. Okay, so if you understand, so you can just understand the one that you care about by understanding a simpler one, and the map between them. And this can give you lots of information. And in this case, so this gave a few things. So these corollaries, you can compute some invariants. So you can compute that the integral Chow ring of M12 bar. So this is isomorphic to Z of xy divided by 24 x squared plus y squared comma xy. This description can tell you what is the integral Chow ring of M12 without the bar. So this is just Z of t divided by 12t. And so here the map from the integral Chow ring of M12 bar, the restriction to the integral Chow ring of M12 is the one which sends y goes to 0 and x goes to t. Okay, and maybe the last thing I can say here is that using this explicit description, you can compute the Brouwer ring, so the Brouwer group of my M12 bar over any scheme S, and such that, so now this is the only part where I'm working in arbitrary, over an arbitrary base, and I'm demanding that 6 should be a unit in S. And so this is the same as the Brouwer group, of the cohomological Brouwer group of the base. Okay, so what am I trying to communicate here beyond all what is written on the, together with all that is written on the board? I'm trying to communicate why these results are interesting about the birational geometry of these moduli spaces and doing these constructions, because these contractions, because usually you can, whenever you contract, you cannot simplify the situation. And this simplification allowed me to compute a bunch of cohomological invariants of my moduli space based on a simpler moduli space and on knowing precisely how the map between the two is. Okay, yeah, so this is, I have 5 minutes, I think, and I have 1 minute, and so this is all I want to talk about.
Thank you very much for the interesting talk. So are there any questions?
Oh, that's a good question. Let's see. So here you would take like some representation and you remove the origin. I think I haven't thought of it. It's an interesting question. Let me see if there's some quick way to think of it. Yeah, I'm not sure. I think it's an interesting. Yeah, I'm not sure. I would have to think of it a little bit. Yeah, I don't know. It's a good question. Thank you.
Do you always have an explicit expression for Z, like in the proof of Castelnuovo?
No, but I can say a few. Maybe let me say how Z is constructed, roughly how Z is constructed. Maybe, yeah, let me say roughly how Z is constructed. So essentially what you do is you first look at the coarse moduli space. So you have your Y, and here you have your E, and here you have your X. And remember that these, like locally have that quotient presentation. So this maps to my little X, and this maps to my little E, and this maps to my little Y. These are the coarse moduli space. Remember, this was the map that etal locally, like locally on this is just a quotient by a finite group. This is the kind of X I'm putting it here. So these are just varieties. I mean, you can think of them as they are varieties. And the first step is to construct some Z here. Not curly, but just a Roman Z here. And this Z is constructed, is kind of explicit. It's constructed using Artin's algebraization. So this doesn't come, so okay, maybe one answer is that this is not quasi-projective variety. It's not proj of something like in Castelnuovo. You can just construct locally, but the local structure, you can write it down explicitly. So the Roman Z, you can construct it explicitly. And then we show that once you have the Roman Z, there's only one way for a curly Z that you can put on top. So in that sense, it's kind of explicit, but it's definitely less explicit than in Castelnuovo. Since Castelnuovo, you really have a line bundle in right proj, and that's your X prime or like the Z. Here, this might not be projective. So you can just, locally you can describe it, but globally is much more complicated. And once you know Roman Z, curly Z, we show that you have only one choice for curly Z, essentially. Yeah, that's a good question.
So in that diagram, so I think vertical arrows are already isomorphisms.
These ones here?
Yeah.
Oh, so this is the complement of the origin. So this is open embedding. Yeah, like the way to think of it is pretend that the action is 1-1, and here I'm just saying that if this was a 1, this was 1, P1 is just A2 mod GM.
So the bottom horizontal, the bottom horizontal map already is rational instead of.
Oh no, so this one is actually amorphous. This one is my F here. And this is not defined all over because the preimage. So here the preimage is. So here this is just a complement of a point.
So you okay.
But the preimage,
yeah. Something maps to a point.
Exactly. There's like a cusp mapping to a point. If you check, it's the locus where this. The locus where A4 is 0 and this other thing is 0 is mapping to 0.
Okay. Okay. Thank you. Are there further questions? Yozen, do you want to ask some questions about moduli space of curves?
No pressure.
So in your theorem, you have child group of n bar 1, 2 to the non-bar 1. But why you have that map?
Yeah. So this is whenever this because this is an M12 is an open inside here, and what you can do is you can take an element in the Chow ring and just restrict it, and one can give an interpretation of what X and Y are in terms of Hodge classes. There is a geometric interpretation on them. I don't remember it. I'm not sure if this is related. Yeah, this is just a general fact that whenever you have, say that you have, say X, which is a quotient stack, and then you have U, which is an open. Then you have a map from the Chow group of X the Chow group of U, Chow ring of X to the Chow ring of U when say X is smooth and a quotient stack. But this is just the general fact that you always have a restriction map. You can think in degree 1, you kind of think you can kind of think of it in terms of the Picard. Like whenever you have like for A of 1, this is just the Picard group. So what you're doing is just you're restricting a line bundle, and the same story goes through in all the ends. Yeah, good question.
Maybe one last question. So your main result holds in any characteristic?
Okay, so my main result holds in, so what we write is, I think.
For tame.
For tame, for sure. Yeah, I think tame, so K doesn't need to be algebraically closed, but you need the tame, which in practice, what does it mean? It means that the curly X should be tame. Essentially all the stabilizers, if you, it's tame. Yeah, for tame,
if the stabilizer co-prime with the
the
characteristic, okay.
Yeah, or the representation theory of the stabilizer should be good essentially. Yeah.
Mm-hmm. Okay. So are there more questions?
But again, all the content is really like there isn't really anything new for the tame part. Like how the proof went is that we proved over C, and then we look at the proof, and okay, we can just say tame, and the same story goes through. There is not really, if like the content is really over C, but the proof goes through for in a positive characteristic too.
Mm-hmm. If there's no further question, then let's thank Giovanni again. Thank you very much.
Thank you.